Hi everyone. Before I start the first experiment, the torsion test, let me remind you of these two basic equations in solid mechanics. When an element is under normal load, we would have normal stress and we would have changes in length, which we call strain, normal strain, and we show with epsilon, and we have this relation between normal stress and normal strain. E is Young modulus or modulus of elasticity. When the element is under such load, we would have shear stress and there would be changes in angle. So this 90-degree would either increase or decrease after this load is applied. Changes in angle would be shown with gamma, shear strain, and we have this relation between shear stress and shear strain. And G is called modulus of rigidity, or shear modulus. Both of these equations are valid only in elastic region. So in elastic region, when the load is removed, all the deformations that the material is undergoing would be recovered, and the material would get to its original length and angle. In the torsion test, a cylindrical shaft is placed between these two ends. One end is fixed, the other end is rotating. The angle of rotation is read from this traptometer, which is shown in a zoomed-in view here. You apply a torque using this torque wheel, and then you would read the angle of rotation from this traptometer. A strain gauge is attached to the middle of the shaft, which you can see here. This strain gauge is measuring the strain along these three directions, and these three directions are 45 degrees with respect to each other. So from this strain gauge, which is connected to this strain indicator, which is shown here, from here you would read epsilon 1, epsilon 2, and epsilon 3 along these three directions. And from there you're gonna measure shear modulus, and from shear modulus you can get what the material is. So I would post the properties of different materials on Moodle, and from that reference you can guess what this material is. And this one is showing the torque gauge, which is placed here. And whatever you read from this dial, you need to multiply by 11, and the result would be the torque in inch pound. This figure shows how the torque is applying shear strain to these surface elements. So these 90-degree angles are either larger or smaller. So we have shear strain here. And this is the data sheet that you need to fill out during this experiment. The relative angle is read from the traptometer, epsilon 1, epsilon 2, and epsilon 3 from the strain indicator at different applied torques. And this figure shows the relation between angle of rotation and shear strain. So as I said, shear strain is changes in the angle when a shear stress is applied to an element. So here you can see we have gamma and phi and the relation between them. This equation shows the relation between the rotation angle and the torque that you're applying to the shaft. So we have torque with the length of the shaft, which is about 18 inches. J is the polar moment of inertia of the cross-sectional area. For cylindrical materials, we have this formula for J. And then from this equation, you can calculate G. You need to plot the angle of rotation with respect to torque at different torques, and then the slope would give you the shear modulus. So shear modulus can be calculated here. Now if you consider two elements on the surface of the shaft, one element parallel to the axis, the other at 45 degrees to the axis. So for this parallel one, we only have shear stress. For the other one, we only have normal stress. So in this experiment, we don't care about this direction, we only are considering this direction, and we're calculating this maximum shear stress that we have here. And it is given by this equation, torque multiplied by the radius of the shaft divided by polar moment of inertia for the shaft, cylindrical shaft. So this is what you get for as the analytical value of shear stress, and then from the strain indicator you obtain these three epsilon 1, epsilon 2, and epsilon 3. So from here you can calculate shear strain, and as you remember, we have this relation between shear strain and shear stress. So you need to multiply this shear strain by modulus of rigidity and get this shear stress. This is your measurement, and you're gonna compare your measurement with the theoretical, analytical value of shear stress. So epsilon 2 is usually considered 0, but in this experiment there might be some misalignment, some slight misalignments of the 45 rosette or the shaft itself, and so epsilon 2 might not be 0. So we don't, as there's no load applied in axial direction, we don't expect this shaft to change in length in x direction. But after you do the experiment, you would get some non-zero values for epsilon 2, and it would make some deviation from the theoretical value that you finally get for shear stress.